Let me talk a little bit about image calibration and flat field images in particular. Whenever we take pictures, say of a flat field, we're getting two basic pieces of information. And I'm going to bring up a new word here, but I think it encapsulates the idea that seems to be getting many people confused. You take a picture of a flat field, you have light, some source of light that's illuminating your chip, you got light. And you also have an electronic signature that the chip, the electronics are producing. And that signature could be called a bias frame, or we could be calling it one of these flat darks, for example. They have different names because the kind of information that they contain is a little bit different if you choose to define them in that way. But they are both electronic signatures, and they are both subtracted from a flat. So there we have it. In fact, let me try to be even more specific. I'll bring this up here. There are two reasons that you can use a bias frame, and I should really call this then, I'm trying to convince you the more general name for this might be to use an electronic signature. That is, a picture of the chip at a particular time, what electronically it is doing. That's the electronic signature. So the electronic signature then, it can be used to subtract from a flat, or you can subtract from a dark frame for purposes of this kind of more specialized way of taking advantage of the linearity of these chips is dark frame scaling or optimization. This allows you to use darks that are at different times, different time exposures compared to your data. Those are the only two reasons, and they're separate. So if we're not doing this thing here, which is in general most people are not, then the only thing that matters is the first part. That's it. That's the only reason we're using the electronic signature, the bias. It is just to subtract from the flat field. So I am now defining a bias or any other kind of short exposure to be this electronic signature. A dark frame, when you take a picture with the shutter closed, it has the electronic signature plus any extra dark current that happens through time. The dark current is just the accumulation of additional electrons that are on top of what the electronic signature has when you take an exposure for that time. Then we also have this idea of a the flat field image. Again, it has the light plus this electronic signature, and so we need to remove that before we can use the flat. So the calibration math is the following. This is the way it works when you calibrate an image. You have a light frame of a galaxy. You subtract the dark frame. Now you subtract the dark frame because it contains two pieces of information right here. It contains the electronic signature and the dark current all together. This is why you do not want to subtract the signature again from this thing, not unless we're doing something like this thing up here that's handled differently. We don't double subtract the bias from a dark frame. That can lead to problems. This is one of the things that you look out for. If for some reason you have doubly subtracted the bias, then a little bit extra comes out of this light frame than should have. And that will mess things up, especially with regards to numbers and other things. So we don't want to do that. And then once you've subtracted this, everyone knows this part. You have to subtract the dark frame. And then it's the second part of the equation, which is you divide by the flat field image. You're actually dividing. After you do the first part here, then you divide that answer by the flat. Now you divide by the flat times the average intensity of the image, but you're dividing by the flat times some constant. But you divide by that flat times some constant. But you have subtracted this electronic signature from the flat before you use it. So in the case of a normal CCD camera, this electronic signature we call a bias frame. That's 0-second exposure. It has that electronic signature you subtracted. Now the unfortunate thing is that for CMOS, I think it's unfortunate, for CMOS chips, the electronic signature can change with exposure time. So that means that I can't just take a 0-second exposure and affect it and expect it to work for my 5-second flat or my 2-second flat. So I actually have to have an electronic signature that is the same time as my flat field image. So now, is that a dark? Not to me. That's not a dark frame. A dark frame has dark current, period. That's semantics. It's an electronic signature, I agree. But a 2-second, what would be called flat dark, does not have dark current. It may be dark in the sense that the shutter wasn't open, but that's not what dark means here. Dark means, in terms of a dark frame, we're looking for the current, the dark current. That is the additional signal coming from these electrons through time. That does not happen in a 2-second exposure. So I prefer to think of, in my head, as a dark, a flat field dark, if you will, a flat dark, as an electronic signature at a given time. So that, of course, we do subtract from the flat, just as I have here. We call it a bias or not call it a bias. It is functionally the same. We are subtracting that value just as we would a bias frame. This is an important thing to recognize, and I will be referring to it in just a moment. Now, let me just say something that's a little bit more advanced. Remember a moment ago I said that this is how you take care of the flat field image, but technically, in order to keep everything correct, you have to multiply this times the average value of the flat, or median value, or mean value, or whatever it is, but it's times some constant. The point is that this thing here, you can just call it a constant, C or K, whatever you want to call it, some number. Here's what happens. This, when you subtract here, if you make an error in adding or subtracting this electronic signature, let's say you didn't do it, or something like that, this multiplier here makes this error bigger, potentially a bigger deal than it otherwise would have been. So the very fact that we have a multiplier here as part of the calibration process is what makes those flats do funny things when we don't get this electronic signature correct. That's where this comes into play. But the more important thing to understand is that the error itself, whether we get the flat correct or not, or even if we get our dark frame correct or not, those are all plus and minus some number. It's only plus or minus some number. That's it. Adding or subtracting things. So that when we look at an image that looks like this, we say, assuming that there's no gradient, assuming this is not vignetting, assuming all of those things, that this is simply an over or under correction. And I guess I can, in some way, kind of prove that to you, or at least we can probably reach that conclusion. If we look here at the flat itself, it does take a similar kind of form, where you'll notice here we have, look at the corners here of the flat. The corners here of the flat are dark, but in the data that was calibrated, they're bright. And then as you move inwards, as things become brighter, here things become darker. That is what you would call an overcorrection, because the thing here that was supposed to be dark, or excuse me, that is dark in the flat, this is the non-uniform illumination. We expect that the flat in our data is going to make these values a little bit brighter, but it made them a lot brighter. And in the same breath, I would say that the flat should make these values in our data a little bit darker, but it made it a lot darker. That is how I claim that this is an overcorrection. You can have an undercorrection, of course, which just does the opposite. So what I'm going to do now is, let's say I couldn't and I did not identify quickly what the problem was with this data. I didn't. But I knew something. I knew what I just showed you, the math, which is that adding or subtracting from a flat is going to change whether we get an over or under correction of our data. I knew that. Even if I don't know the source of the problem, I knew at least I could fiddle with that. So that's what I did. I fiddled with it. I tried to figure out, well, what do I need to do to the flat to help undo the overcorrection? Well, what that means is that these values here in the flat, effectively, let's say in the corner, if I don't want them to overcorrect, they need to be a little bit brighter. So I knew that I needed to add, for example, some constant value so that added to the flat so that it would probably work in the correct sense of the correction that was necessary. Remember, there's a multiplier here, the way that it works, and that multiplier is going to affect, this. I had a 50-50 chance. Let's just call it that. I had a 50-50 chance of getting it right, and I decided I was going to add to the flat and see what happens. So I'm going to take you through that process. The important thing to take away from what I'm about to show you is that this is a method of tuning flats. If you have a flat which is very close, but maybe it is over or under correcting, your data may be absolutely perfect. There may be nothing wrong with your calibration data, but you still have an over or under correction going on. This is something you can do. So here's what you do. I'm going to first open that master flat, actually, the one I just had open. I closed it. There it is. And we're going to get out pixel math here. So I'm going to find pixel math. And we're going to choose some small number to add here. Now, what number? I didn't know, but I knew that if the number were large enough, I'd probably be able to see a difference. So I'm going to say 0.2. So I said target t plus 0.2. I am adding a number to the flat here. There we go. Now I'm going to save this, but of course I'm going to save it as a new creature. So I'm just going to add something here. I'm going to say underscore 0.2. That's just indicating to me that I've added 0.2 to that thing. Now what I'm going to do, I'm going to close this. I'm going to rerun this. I'm just going to run it again. And you don't even need to watch it. I'm just going to run it again and show you the result. So let's do that. So execute. There we are. Now, most things are loaded here. What I don't have correct, I'm going to need to reload that set of darks. I really should save another process here so I don't have to keep doing that. But what I'm going to change this time is the master. I'm going to say, okay, let me just show you. Hold on. Let me just do everything here. So we're going to add those. Coming back to here. I need my signatures for the flats, electronic signatures. There's a nice word. We will make them darks like that as a type. 1.08. There it is. So that puts them in the right spot. We have our flats here, but I'm actually going to clear. I'm going to clear all of these things. So I'm going to clear the flats, bias the darks. The dark is, I guess I'll have it redo the darks. The light frames are here. Okay. So we don't have a bias. It's going to redo the darks, but for the flat, we're going to use a master flat. And of course, what we're going to use instead of the one that was before, that's the one it made, we're going to use this one. It's the same thing. I've just added that 0.2. So now everything should be the same as last time, except that I've added a little something to this master flat. So having done that, let's be sure. Oh, the output directory, I should have. I forget to do everything here. I am going to put this in a slightly different place. So this was going to be, this will be my test area. I'm testing the results, right? Diagnostics, it should complain about the bias. That's fine. Run. And that's okay. So I'm going to go through this process of calibrating the data, then aligning it, combining it in exactly the same way. I might come back and show you that I'm going to do nothing else other than press these buttons here, because I'll basically be loading similar files, or at least the same settings. I'll have to reload the new calibrated frames, of course, and then produce another result here. Okay, so it completed it. I'm going to go ahead and just save another process here. So the latest and greatest process is here. I'll keep this one, or actually that one. This one I'm going to delete. Okay. But this is the new working one for me. Anyway, I'm going to go ahead and do the alignment. I can even keep the same file as a reference. It doesn't matter that it happens to be in the other set. Or I could be self-consistent. Yeah, it will be consistent. So let's go ahead and get the reference. So in John, but we want to go into the test area, calibrated light. So there's the reference. And then I'm going to add these files here in the test area. This is the directory I need to change. Calibrated light. Make my new registered directory in here. And then off and away we go. Okay, and then clear here. I'm going to add test area these files. Combine them, and the idea here is that this image should be different. The integrated image we get now should be different than this one, because what I'm doing right now is I am just messing around with this value, this electronic signature. I've added a little bit of a constant value to every pixel. That's all I've done. So it's a perfectly legal thing to do, in the sense that if we're doing the same operation with this constant to every pixel, it's not like we're changing the relationship between pixels, but we are going to change how that flat interacts. Because really what it's doing here is I'm making the difference between the very brightest things and the dimmest things. That ratio is different. See, if I add a value to things that were already small numbers in the flat, it makes a big difference compared to adding a small value here to numbers in the flat that were already quite big. So that's how we get this slightly different effect between the edge of the frame and the center. So let's see if there is an effect. Now, isn't that interesting? I will blink the two images, and we do a before and the new version after. I am just hoping, I can't hear you out there, but I am hoping you're impressed. If you have not had the opportunity to tune your flats before because you have a simple over or under correction, this is what you can do. You can do this blindly without even ever having to try to, solve the issue or find the problem. It's not completely there, though. I still notice by eye that this is still dark here. Now you got to remember, in a single frame, even the worst case, the ones that I used to integrate to make this result, in a single frame you really couldn't tell. And so now in this, what would presumably be improved frames, you still couldn't tell that what the end result was going to be until you actually followed through on the processing and integrated a new result by adding many frames together. So it is visually in this integrated result that I'm looking, and I can say that it still needs to be a bigger number. Now, what the number means without investigating something more about the data and the problem, I couldn't say at this point. But I can say by brute force, we can probably make it there, because you'll notice that we had a decrease in brightness here in the corner, and we had an increase in brightness here, though not enough. We didn't have enough of either. So just for fun, I'm going to reopen that original flat. So this is our adjusted flat, but this is the original. And based on what I saw, well, that's the blink tool. Where's the, I don't know where the pixel math went. I'm going to add a bigger number using pixel math here. Instead of 0.2, let's try 0.35. We're going to go wild. So I add 0.35. Let's make sure it said too many decimal points. Yeah, there are too many decimal points. I wondered why nothing happened. Okay. I'm not displaying it, you know, back to where it should be, but File, Save As. So this one, we're just going to say 0.35. That's what that means, I guess. And you will not be surprised to learn, I'm going to run this again, but I will save you from having to watch it. So when I come back, I will have the actual result to compare with this, the original. So one moment. Just to be sure you're understanding this, I'm going to clear this master flat and simply load this new master that I've made. And then everything else will follow. I'm just going to overwrite the previous files. There's no sense in keeping any of that. Well, our darks are not bias subtracted. This is just a warning. Apparently it comes up without, it's not actually examining our darks. It doesn't know. But we don't have biases. We didn't use biases. So the master darks are straight up darks. They have the electronic signature within them, and so they will subtract directly to our lights, which is exactly what we want. So the only adjustment here really was the adjustment to that flat, the flat field image, the master flat anyway. Okay, moving right along, we'll exit out of here. Oops, I meant to say yes. And we need to do star alignment. I overwrote those previous frames. So this time star alignment is fine, but what I'm going to do in the test area, just to be absolutely certain there is no question about these are new frames, I'm deleting the previously registered frames. So now when I create new registered frames, they are fresh. And then, of course, finally, we do our integration. And here it is. Let's see if 0.35 gives us an even better result. Indeed, it does. So this is a method, even though I have not yet identified, I haven't shown you what the problem is, even without knowing the problem, if you find an image that just has simple over-under correction, this is a way to basically tune your flats. This is a way to actually do a kind of diagnostic to flats, because even if, for example, there were other problems with non-uniform illumination and things like that, if you know you've tuned it to the best possible, your ability to do so, then everything else that remains is not because of an over-under correction, it's something else. So let's blink. Here's the before, or the before and the after. And maybe you can argue I went, maybe it's 3.3 or something. But it doesn't matter. This is now, I think you would agree, very usable data that would require only very minor, if any, adjustments with DBE, for example, compared to something that looks like this.